And then now, switching gears. It is about mining jurisdiction, uranium exploration, and geopolitical context in Paraguay. This is given by Emily Hersh, CEO of Luna Energy in Nevada, United States. Emily, oh, here, she's here, okay. Emily was the winner of our entrepreneurship award last night. Congratulations.
Thank you. Thank you, Florian, and thank you to everyone who has decided to join us this morning. I'm excited to share a little bit of what it means to be an entrepreneur in the mineral exploration space, both in the context of looking at the discoveries that are propelling new inventions and new applications of science, but what that means from a mineral exploration standpoint. I don't know if this works for mine, so let's give it a check. It does not, so I'm gonna just give you a cue if you don't mind. So nuclear energy and the demand for uranium has been in the news and in the press and in a lot of topics of conversation recently as demand for a stable source of carbon-free energy for the growing demand for AI and for data centers has taken place. Just in the past few months, you've seen Microsoft, Oracle, Google, and Amazon make large announcements about moving large portions of their energy consumption to nuclear sources. And then you've also seen the growth of small modular reactors and new nuclear reactors that are solving some of the problems that exist in, for example, wind or solar, in that they can provide energy over a constant block of time without a carbon footprint. And so we really are in an interesting age where demand for and the technology behind nuclear solutions to some of our energy challenges are a reality, but those are also taking place along a backdrop of a Cold War-esque mentality, where you've seen the United States and some of the European nations, and as well as Canada and Australia, look to decouple their supply chains from Russia, from Kazakhstan, and from China. Next slide. So you'll see here that in the levelized cost of energy standpoint, you see that nuclear is on a very favorable place. So if you were to stack nuclear up against other forms of electricity generation or other forms of power generation, you'll find that nuclear is the lowest cost solution that provides energy without a carbon footprint. And so what that means is that many of the ESG or environmental and sustainability-driven either groups or sources of funding or government regulatory practices have you can see over to the right-hand side, that they have stopped excluding nuclear energy as something that they're willing to invest in or willing to put into their own energy mix. But then when you look at the breakdown of where does this nuclear fuel come from, you see over here in this pie graph that the concentration is extremely geared towards Kazakhstan and other countries that are not necessarily in the US or in the European orbit of geopolitical control today. Next slide, please. And so this slide kind of ties together what we see looking at the macro level demand for uranium feedstock. You see that from where we are today until 2040, not only do we have uranium demand increasing because of the themes that I just covered in the last slides, but we also see that the capability of today's current supply chain is dwindling or is going down. And that's normal in any mining life cycle. Mines are, by definition, non-renewable resources. They have a life of a mine that may be 20, maybe 40, maybe 60 years, but in order to continue producing whatever raw material that is necessary for whatever application, there is a necessity for not just mining, but for companies like Luna who go out and do exploration activities to discover and to characterize new resources around the world. Next slide. When we talk about a mine, or we talk about any mining project, I like to use this graph, and it's especially important to take a look at the concepts along the bottom. So we think about mining as, okay, we need this thing, we need this material, we're going to build a mine. But in reality, the life cycle of a mine, from concept and discovery through startup, typically takes between 15 and 17 years, and that's if everything goes right. So if market conditions stay favorable, so that the ability to finance a new project remains constant throughout the life cycle, that means that from a regulatory standpoint, a company is able to meet all of the requirements to bring a new project online. And that means that the pricing environment for the commodity stays roughly stable. So in reality, most discoveries through a mine take multiple economic cycles. So it can be between 20, between 30, between 40 years from when an initial discovery is made to when the conditions are right for that material to be taken out of the ground in an economically and environmentally sustainable way. Next slide, please. Luna is focused on Paraguay for uranium exploration. And Paraguay is a small country. It's located, as you can see here on the map, it is south of Brazil. It's to the east of Bolivia, and it's to the north of Argentina. And while Paraguay doesn't sort of come onto most people's minds as the first country they think of for doing an exploration project or even participating in a new energy paradigm, Paraguay is a stable and pro-business market that has had the most consistent growth from 2004 until 2024. It's a country with very transparent tax, regulatory, and mining laws. And it's also in an extremely central and logistically prominent location within the continent. So Paraguay is home to the third largest fluvial fleet in the world because of the river transport that exists, given its proximity to Brazil and Argentina. It has $39 per megawatt hour electricity, which almost all comes from hydropower. And it's a member of the Mercosur trading bloc, meaning that it would be allowed to sell feedstock into countries like Argentina that actually currently have a very active nuclear program. So from a uranium standpoint, and also from an ability to do business standpoint, in a sustainable and environmentally sustainable way because of the electricity from hydropower, because of the ability to transport via rivers, and because of the ample access to the kinds of things you need to do projects like this safely, such as water and logistics, it's a great place to be working. Next slide. So this is just an overview of the projects in Paraguay that my company is doing exploration work on. You can see that they're over on the eastern half of the country. And now I'm able to get into the part of the talk that I really like, which is the geology, to explain why these are the areas that my company is exploring and what we hope to find there. Next slide. So when you look at geology, and when you talk to geologists, you have to think about geology like very, very slow, extremely old chemistry. Because what we do as geologists is we look at the Earth and we try to understand from the top and then down deep into the Earth how the rocks that we find or how the sediments that we encounter formed and what deposition mechanisms and then later concentration mechanisms led to the deposits that we're trying to identify. So Paraguay is located in the Paraná Basin, which formed during the Paleozoic and Mesozoic eras. And it comprises both sedimentary and igneous rocks. So if you look at the table to the bottom of this slide, you can see that the area or the region is correlated with its neighbors in both Brazil and in Argentina. And it's a record of the Gondwanian glaciation that was then followed by the decline of the glacial conditions in the Middle Permian, and that made the coal deposits that you see in South America possible. But then it was followed by a marine transgression and the deposition of schists, silites, sandstones in a lower marine platform environment. And so if you see here on this table, you can see that in Paraguay, the formations that we're looking at, which are the Misiones, the Independencia, the Coronel Oviedo, and the San Pedro group, are correlated with the same units in both Brazil and in Uruguay that host these types of known uranium deposits. Next slide, please. So the key features of why we selected the areas that we're working in to do exploration is that as part of that Western Parana Basin, you have these known sandstone-hosted uranium prospective areas, but also that there are crystalline rocks that form the potential for uranium deposits that would be more similar to what we see in Canada, that are related to the acidic intrusive rocks. So these are the two main groups here that we're looking at, but you can see that this is a geological map, and the geological map shows you the age of the rock that's at surface. And so correlating these with the geology of the neighboring countries and understanding how that came together, how it was deposited and when, and what mechanisms caused it to move around, which might have been the primary driver for the depositional or concentration mechanisms that lead to mineable uranium deposits. Next slide, please. So there are two major kinds of known uranium deposit models. The first, and the one that is already known to be in Paraguay, is a roll front style deposit model. And these are formed at the interface between oxidized and reduced groundwater in permeable sandstone aquifers. So they're called roll front because they typically have a crescent or roll front shape when they're in cross section. And we're able to explore for these using geophysical methods, but also doing water and sediment sampling to understand not just the precise data point in one place, but putting the data that we're able to collect over the country in context. Next slide, please. The other deposit model is called an unconformity type deposit model, and these are a genetically diverse group of ores that form with a wide range of intrusive rocks with petrochemical compositions. So these are different uranium minerals that are found, and they're divided into anatectic ores and plutonic ores. But these will typically be much higher grade in uranium, but much smaller and much more specific locationally, so a little bit trickier to find. Next slide, please. This is an overview of some uranium deposits that are currently either in exploration or in development or in production worldwide. As you can see, the size of the resource and the grade of the resource varies greatly, mostly via the deposit style. So I think that one of the things I tried to explain from an exploration standpoint, it's not so much that one deposit type is better than another deposit type. It's more that understanding what deposit type you are working in and how that could make a project in the specific circumstances of where you are is important to understanding both the market and what kinds of exploration techniques that you need to deploy. Next slide, please. So Paraguay has a very interesting exploration history. And this is sort of the ability for a company like me to come in and run the program that I'm doing in the modern era comes from the fact that from 1976 to 1983, a US company called the Anschutz Corporation undertook a countrywide, full eastern side of the country survey where they did a substantial amount of drill holes, as well as airborne radiometric surveys, airborne magnetic surveys, scintillometer, which is like a Geiger counter, both truck-mounted and handheld, as well as track etch, which were radon gas detecting surveys, and water sampling programs. And so I'm able to take that data that was acquired quite some time ago, but apply modern techniques to understanding what it might mean in the geological context of where I'm working. Next slide, please. So this is what the historical data that I am working with looks like. And unfortunately, my team has received all 32 gigabytes of it as one-by-one scanned pages in no particular order, with quite a bit of, as you can see, hand-drawn notation as well as internal company coding. And so the process of digitizing this, I've laughed and rolled my eyes a little bit at some of the folks who want to apply an AI model here. Because it really is more like the job of an ant in that we have to go through everything and then try to start putting things in context. And once we identify areas that we think are interesting, go back and look for data that was collected in those areas or near those areas that might give us a clue as to why something in one place is just a little bit different from something else. Next slide, please. So this is where you can see that we've worked through correlating some of the drill holes. One of the interesting things about uranium exploration is that because of the radiometric signature, instead of just doing geochemistry on the cores or on the physical things that we take out of the drill holes, you're actually able to use gamma ray spectrometry and do downhole geophysics. And so part of how you look for continuity along a series of drill holes is by seeing where and how the peaks align as they are vertically aligned. So this is just an example of my team that's done that on one very small part of one of our areas. Next slide, please. This is the map here that is the product thus far of all of that work to date. And as you can see in our blocks, we are working with identified uranium anomalies, some of them identified using water data, some of them identified using ground gamma ray data or scintillometers, some of them from drill holes, some of them from track etch, which is looking at radon gas captured slightly below surface, and then some of them from historic airborne surveys. And so the historic airborne surveys is a very good example of where methodologies today would differ very, very importantly from what was done in the 70s. So in the 70s, these airborne surveys would have only been able to penetrate the first meter. Whereas if I were to fly these surveys again today, I'd be able to get down almost a kilometer or more. And that means I'd be able to identify some of the graphite conductive pathways that may exist in the bedrock that may give me clues for the channels along which this uranium mineralization would have taken place. Next slide, please. These are the areas that are prospective due to their proximity to known uranium deposits. And these are the areas where I'm able to layer on geological information on faulting and structure that wasn't available historically, and to understand why and how I might be seeing mineralization trends curving in a certain direction, or why, for example, you would have seen track etch anomalies start and stop somewhere where the water then began. And so this is an area that we are going to be doing exploration, predominantly looking for roll front style sandstone-hosted deposits. Next slide, please. Next slide, please. Whereas these areas that are further to the south have a geological context that involves more crystalline rocks. And this is an area that there was not as much on-the-ground exploration performed historically, but you do have that radiometric and water sampling data. And so this is an area that we're going to try to fly new airborne geophysics to see if the anomalous uranium geochemistry corresponds with some of that more deep structural geology, and if there is prospectivity for the inconformity style or crystalline rock linked uranium formations. Next slide, please. This is another just example. It's a similar thing, but you can see here how on some of these areas we're working with drill hole data, which is subsurface geochemistry and subsurface gamma ray scintillometry. But some of these other areas that we're working with are airborne radiometry and or water targets. So it's a very interesting and exciting challenge for my team and my local geologists and then the geological teams that I bring in to guide us and or give us a hand with processing some of the data or putting it in context. Next slide, please. So this is just a summary of the areas, and one of the exciting things for me as a CEO and leader of this exciting project is that almost every week we identify additional drill holes that were on our property, and we are able to find more gamma peak and depths that they occurred at and align them with some of the geochemistry from the drill holes that is also favorable. Next slide, please. So this is just a little picture of what Paraguay looks like. It's got easy to work in topography, which anyone who's ever worked in exploration or taken a long trip knows there's a big difference between driving 5 kilometers flat and 5 kilometers up and down a very craggy mountain. As you can see, we're doing the work with Nissan Frontiers, and that's what I like to say about Paraguay. It's so easy to do exploration, you don't even need a Hilux. You can do it with a 4-cylinder diesel truck. And this is my team getting out and doing the field work to not only collect new data or collect data that would support the historic data that we currently possess, but also to do the very important work of getting to know the people who live there, who live around there, so that my company is able to continue successful operations for a long period of time. So this is my last slide, I think. One last. There we go. So thank you very much for your time, and if any of you in your labs are doing research that involves geochemistry or geophysics or new exploration techniques, I would love to talk to you. I love to take on interns and or research project students in the areas that I work, and this is mining, it's not just for old prospectors who are the bad guy on Toy Story. It's the foundations of everything that we are able to enjoy in modern life today.
Thank you very much. How long you've been in this project?
I've been in Paraguay for 3 years now.
3 years?
Just started the uranium project.
Okay. Let's have a picture for the record, as we'll always do. Congratulations again. Thank you.